Imagine we had a biased coin, where the probability of throwing a heads was 0.7. Then the probability of throwing tails must be 1 subtract 0.7, which is 0.3. Now let's imagine we throw this same coin 4 times. And we say that x is a discrete random variable representing the number of heads shown on the 4th throws. We could use your knowledge from the previous video to create a probability distribution for this situation. We'd have the x values, which go from 0 to 4, since you can throw anywhere between 0 and 4 heads, and then we'd need to work out their probabilities. Let's do this now. We'll start with the probability that x is equal to 0, which means we throw 0 heads. If we throw 0 heads, all of the throws must be tails. So we've got the probability of tails, 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 tails. If the first throw is tails, that has probability 0.3. The second throw is also tails, so we'll multiply this by 0.3, and so are the third and fourth, so multiply by 0.3 and 0.3 again. So this probability is just 0.3 to the power 4. For the probability that x is equal to 1, we're going to throw 1 heads, and then have the rest as tails. Now there are different ways of doing this. It could be heads, tails, 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 or tails, heads, tails, tails, or tails, tails, heads, tails, or tails, 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 heads. Let's work out these probabilities. So for the first one, we're going to start with heads this time, which has probability 0.7. Then the second throw is tails, so it's multiplied by 0.3 again. And so are the next 2 throws, so 0.3, 0.3. For the second one, we start with tails, so 0.3. Then we have a heads, so 0.7, and then 2 more tails, so 0.3, 0.3. For the third one, it's tails twice, so 0.3, 0.3, then we have the heads, 0.7, and finish with tails, 0.3. And for the final one, it's tails, 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 so 0.3, 0.3, 0.3, and finally heads, 0.7. You might notice that each of these calculations in the brackets is essentially the same, just in a different order, but they will give the same result. So we could rewrite this as the first bracket multiplied by 4, since this calculation occurs 4 times. Since these are all multiplied together, we don't actually need the brackets either. And we could write 0.3 multiplied by 0.3 multiplied by 0.3 as 0.3 to the power 3. So the calculation becomes this. For the probability that x is equal to 2, we would now need 2 heads, and therefore also 2 tails. There are even more ways of doing this one. We've got heads, heads, tails, 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 heads, heads, tails, 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 heads, 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 tails, tails, heads, heads, tails, heads, tails, and tails, heads, tails, heads. For this one, we can speed up the process since we know each of the brackets is going to give the same calculation, so we'll just do the first one and multiply it by 6 since there are 6 of them. For the first one, we would have heads, heads, so that's 0.7 times 0.7, or 0.7 squared, and then tails, tails, so 0.3 multiplied by 0.3, which is 0.3 squared, and there are 6 of them, so we would multiply this by 6. For the probability that x equals 3 then, we would have all of these combinations, which is 3 heads and 1 tails. So we take the probability of heads, which is 0.7 3 times, so 0.7 to the power 3, and the probability of tails once, so just 0.3, and there are 4 of these, so multiply this by 4. And finally, for the probability that x is equal to 4, we would have heads each time, so it's heads, 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 heads. So we'd have 0.7 multiplied a total of 4 times, which is 0.7 to the power 4. So the probabilities will just be the following. If you work these out on your calculator, you'll get these values here, which will allow us to complete the probability distribution that we started earlier. This type of distribution has a special name, and it's the title of the video, the binomial distribution. There are a few requirements for a binomial distribution. Firstly, we must have a fixed number of trials which we give the letter n. In our example, n was 4 since we threw the coin 4 times. Secondly, we must have 2 mutually exclusive and exhaustive outcomes. Our 2 outcomes when throwing the coin were heads and tails. They're mutually exclusive since they can't happen at the same time, and they're exhaustive since they cover all possible outcomes. Next, we need what we call a fixed probability of success, which we give the letter p. In our case, being successful was throwing a head since that's what we were looking to do. So our value of p was the probability of throwing a heads on a given throw, which was 0.7. It also means we have a probability of failure, where the probability will be 1 subtract p. In our case, that was the probability of throwing tails, which was 1 subtract 0.7, which was 0.3. Finally, we require that trials must be independent of each other. This means that if we threw heads on the first throw, it doesn't somehow affect the probability of throwing a heads on the second throw, and so on. If we have all of these requirements, then we write down the distribution in the following way. This x here refers to the random variable x. This tilde symbol here and the capital B means is distributed binomially. And this n and p in brackets here means with parameters n and p. So you could read this as the random variable x is distributed binomially with parameters n and p. For our example then, we would write down that x is distributed binomially with parameters n, which was 4, the number of throws, and success probability 0.7, the probability that we threw a heads. With this in mind, let's return to the probabilities that we worked out earlier and observe some patterns. When we worked out the probability that x was equal to 0, we did the probability of failure 0.3 to the power 4. We could also write this as the probability of success 0.7 to the power 0 multiplied by 0.3 to the power 4. This might seem strange at first, however we can now view the calculation in two parts. This part here represents the 0 successes, and this part here represents the 4 failures. Let's apply this to the next probability, so the probability that x was equal to 1, which meant we were successful one time. So we have the probability of success 0.7 to the power 1, multiplied by 0.3 to the power 3, since we would have failed 3 times, or got 3 tails. Now if you recall, this wasn't the whole calculation, we also multiplied this by 4 for the 4 different ways of doing this. Heads, tails, 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 heads, tails, 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 heads, tails, and tails, 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 heads. So for the probability that x is equal to 2, we would be successful twice and therefore fail twice. So we'd have the probability of success 0.7 to the power 2, multiplied by the probability of failure 0.3 also to the power 2, and if you recall there were 6 different ways of doing this one, so we multiply by 6. For the probability that x is 3 then, we do the success probability to the power 3, the failure probability to the power 1, and then multiply this by the number of ways, which was 4. And for the probability that x is equal to 4, we'd be successful 4 times, so success probability to the power 4, multiplied by the failure probability to the power 0. Now technically we could also say there was one way of doing the first and last example here, so we could multiply these both by 1. So we can now see these calculations are just the successes, the failures, and then the number of ways of doing this combination. It's clear to see where the 0.7 and 0.3 come from, since 0.7 is defined in the distribution up here. But what about these numbers 1, 4, 6, 4, and 1? If you've already covered the binomial expansion, you might recognize these numbers. They are one of the rows in this triangle here, which is called Pascal's triangle. In Pascal's triangle, each number is generated by adding together the two numbers above it. For example, this number 3 here is the sum of this 2 and 1 here. The triangle goes on forever, so we can just add a new row like this. We place a 1 at each end, since 1 add 0 is still 1, and then we add together two numbers to get the next number. So if we add this 1 and 6 here, we get the next number, which is 7. If we add the 6 and 15 here, we get the next number, which is 21. And if you continue this on, this will be the next row. So our numbers for the number of ways came from this row here, 1, 4, 6, 4, 1. The value of n in our distribution was 4, and this is no coincidence because this comes from the 4th row of Pascal's triangle. You may think I've made an error here thinking this is the 5th row, but actually the first row is called row 0, which would make this row row number 4. If we take these numbers then, 1, 4, 6, 4, 1, this showed us the number of ways of getting 0 successes, this was the number of ways of getting 1 success, and then the number of ways of getting 2 successes, 3 successes, and 4 successes. So if we know this triangle, we're always able to work out the number of ways of doing these combinations. Let's try this with a different example. If we take our distribution and change the numbers, so let's instead of n being 4 make n 7, and let's change our probability of success p from 0.7 to say 0.9. Can we now use this to quickly work out these probabilities? To work out the probability that x is equal to 0, we want to be successful 0 times, and therefore fail all of the other times. Since n is 7 in this case, that will mean we fail all 7 times. So we want the probability of success to the power 0, which we can get from here, that's 0.9, so 0.9 to the power 0, and the probability of failing, which will be 1 subtract 0.9, so 0.1, to the power 7. We then want to use Pascal's triangle to work out the number of ways of doing this. Since n is 7, we're going to go down to the 7th row, remembering that the top number 1 here is row 0. The 7th row is actually the one we generated a moment ago. The number of ways of getting 0 successes is therefore the first number here, which is 1, so we would multiply this by 1. For the probability that x is equal to 3, we want 3 successes, so 0.9 to the power 3, and since there are 7 trials in total and we've been successful 3 times, we must fail 4 times. So we'll do the probability of failure 0.1 to the power 4. We then use Pascal's triangle to work out the number of ways of doing this. So in this 7th row, we need to go along to the number corresponding to 3 successes. We must remember that the first number corresponds to 0 successes though, so it's not the 3rd number, but actually the 4th number, so this 35 here. So we would multiply this by 35. Why not pause the video and see if you can do the last one yourself? The answer for this one is 0.9 to the power 6, multiplied by 0.1 to the power 1, and then we go along to the number corresponding to 6 successes, which is this 7 here, so multiplied by 7. If you type all of these on your calculator, you'll get these values here. So if we have a binomial distribution, we can use this method to calculate probabilities quite quickly. However, when n is a particularly large value, like this distribution here, it becomes problematic. For this one, n is 30, which means we need to use the 30th row of Pascal's triangle, which actually looks like this. Fortunately, there is a way to speed up this process. If we return to the triangle and this number 35 that we used a moment ago, this number was in the 7th row and corresponded to 3 successes. Another way of interpreting this number is the number of ways of choosing 3 items from a set of 7 items, which we can shorten to 7 choose 3. Or even shorter, we use the notation 7 capital C 3 to represent 7 choose 3. So 7 choose 3 is 35. Now it just so happens that your calculator understands this notation and can do that calculation for you. Let's have a look. So on a newer style calculator, to type in 7C3, we'd first press 7, then go to Catalog, down to Probability, and then all the way down to Combination, which is what that capital C actually stands for. We would press OK, and then type in a 3, and then equals, and we end up with 35. I'll also quickly show you how you do this on an older style calculator. It's actually faster. We press 7, then notice where it says NCR above the divide button here, so we press Shift, then the divide button, we get the C, then press 3 and equals, and we get 35 again. So since this function is built into your calculator, you'll not actually need to write out the rows of Pascal's triangle. Let's try and use this fact now to work out these probabilities for this distribution. For this distribution, the probability of success is 0.84, so we want 0.84 to the power 20. Then the probability of failure, which will be 1 subtract 0.84, so 0.16. For the remaining possibilities, and since there were 30 in total, and we've just used 20, there must be 10 left, so 0.16 to the power 10. Then we want to multiply this by the number of ways of selecting 20 items from a set of 30, which would be 30 choose 20. So now we take our calculator and type this in. We have 0.84 to the power 20, and then we will multiply this by 0.16 to the power 10, and then we'll multiply this by 30, and then we need to find the choose function in Catalog, and then 20. And then we'll find that this is equal to this number here. Let's say we want to round this off to 4 significant figures, then the answer will be 0.01011. Feel free to pause the video and see if you can work out the next 2 on your own. For the probability that x is equal to 24, we want 0.84 to the power 24, multiplied by 0.16 to the power 6, then multiplied by 30 choose 24. And that will give you 0.1517. For the probability that x is equal to 27, we want 0.84 to the power 27, multiplied by 0.16 to the power 3. And then we multiply this by 30 choose 27, which will give you 0.1501. So we end up with these 3 answers here. Now, believe it or not, there is an even faster way of doing this. Your calculator can calculate any binomial probability just from the parameters and the value of x. This is actually the way you'd be expected to calculate these probabilities in your exam. Let's have a look at how we do it now. On a newer style calculator, we want to go to Distribution. We want the first option, Binomial PD, and then we go down to Variable. And then we need to enter 3 numbers, x, n, and p. X is the number of successes that we're looking at, which in our case is 20, and n and p come from the distribution. n is the number of trials, which is 30, and p is the probability of success, so 0.84. We press OK, and then come down to execute, and if we execute this, we get the answer, which match what we got before. Let's now go back and do the second question. If we press OK, you'll see it remembers these values, so we only need to change the value for x. If we change that to 24, come back down to the bottom and execute again, you'll see we get the second probability. I'm also going to show you how you do this on an older style calculator. So for this one, we need to press menu, and you'll see the number 7 here is the distribution, so we press 7. And binomial PD is number 4 here, so we just press number 4. And variable is on 2. So it's the same information, just in a slightly different way. We then have x, n, and p to enter again, so x is 20, n is 30, and p is 0.84, and then we just press equals. And when you do this, you'll see we get the same number as we did before. Often exam questions on this topic are given in context. Let's have a look at an example. For this question here, we're told that Niall takes a multiple choice test with 18 questions. Each question has 4 different answers to choose from. Niall randomly guesses the answer to each question. We need to work out the probability that Niall answers 5 questions correctly. Now, it may not be too obvious at first that this question is about the binomial distribution, but let's think about it. For the binomial distribution, we need to have a fixed number of trials, and we can see here that Niall is doing 18 questions, which means our value of n is going to be 18. We also need a fixed probability of success. Well, if there are 4 different answers to each question, and he's randomly guessing them, he will be correct a quarter of the time, or 0.25. So p, the probability that he gets a question right, will be 0.25. We also require that there are 2 outcomes, so he's either correct or he's not correct, and that the trials are independent of each other. Now, since he's randomly guessing them, the outcome of one question is not going to depend on any of the others, so they are truly independent. This means we can use the binomial distribution. Since we're looking at the number of questions that Niall gets correct, we could say let x be the number of correct answers Niall gives. Then, x would be distributed binomially, where n is 18 and p is 0.25. We can now use this distribution on our calculator to work out any relevant probabilities. For this question, we're looking at the probability that Niall answers 5 questions correctly, which is the probability that x, the number of correct answers, is equal to 5. So we just take our calculator, go to distribution, binomial PD, variable just like we did before, and enter the relevant values. X is 5, the number of correct answers, n in our distribution is 18, and p in our distribution is 0.25. We go to execute, and we get this answer here. So if we round this to, say, 4 significant figures, this probability is 0.1988. Now let's try part B. So for this one, we want the probability that Niall answers 7 questions correctly. So for the same distribution, we just want the probability that x is equal to 7. So on our calculator, we can just go back here and change this x value from 5 to a 7. We can press OK, come down and execute this again, and we'll get this answer, which is to 4 significant figures 0.08204. Part C of this question is a little more tricky though. We want the probability that Niall answers no more than 3 questions correctly. So he's allowed to answer 0, 1, 2, or 3 questions correctly, but no more. This means we need to work out all of these probabilities. The probability that x is 0, the probability that x is 1, and 2 and 3. Now fortunately, there is a way on your calculator of working out multiple probabilities at once. Let's have a look at how we do this. If we go back to when we selected binomial PD, we were given an option for list. So if we select list, we're given this table. In this table, we have 2 columns, x and p. We can enter any x values in here, and it will place the probabilities in this column here. So let's enter our x values that we want, which are 0, we also want 1, 2, and 3. So we wanted to do all of these at the same time. When we press execute, we're asked to reconfirm the values of n and p, which are the same as they were before, so we'll just go and execute, and we get these values here. So the calculator has worked out all 4 of these at once for us. Now, since all of these scenarios are valid for Niall answering no more than 3 questions, we would add these probabilities together. So we get this answer here, 0.3056. Now, believe it or not, there is an even faster way of doing this calculation. You may have noticed on the calculator when we selected our distribution, there was another option for Binomial CD, and that's the one we're going to use. Here we go down to variable again. And if we keep our value as 3 and just execute, you'll see we get this number here, which is almost identical to the other number we got. There's just a rounding error, which I'll show you in a moment. The binomial CD stands for the cumulative distribution, which means it's going to add up all of the probabilities up to the number that you specify. So when we entered the number 3 as our x value, we weren't working out the probability that x was equal to 3. We were actually working out the probability that x was any number up to 3. So the probability that x is less than or equal to 3. If we round this number here off to 4 significant figures, it's actually 0.3057. The reason the previous calculation gave us a slightly different answer was because it was the sum of these 4 numbers here, which had all been rounded off to 4 decimal places. So it's actually better to use the cumulative binomial distribution when given a question like this. Let's use this information to practice calculating some more probabilities. In this question we have y, which is distributed binomially with n 15 and p 0.57. We want to find the following probabilities. It's worth noting at this point that our random variable is the letter y, but the calculator will only display the letter x, but we just enter the value for y in the place of x. So for question A, we've got the probability that y is equal to 8. So let's take our calculator, and since y is equal to 8, we'll use the regular binomial PD. We'll go into here and select variable, and then we'll change x to be 8, n for our distribution is 15, and p is 0.57. We'll press OK and execute this, and we get the answer 0.1949. For the next question, the probability that y is less than or equal to 8, we need to use the cumulative binomial distribution, so binomial CD instead. So we'll go back and select that, then we'll go down to variable, and we actually have the correct numbers here since we want 8 again, so we'll just go down to execute, and we get this answer here, 0.4847 if we round this to 4 significant figures. So it's important to understand the difference between these two distributions. We use binomial PD if it's equal to a number, and binomial CD if it's less than or equal to a number. But what about if it's just less than? For the probability that y is less than 8, we don't want to include the number 8. So we want the numbers up to 8 but not including it, which would just be the numbers up to and including 7. So this is actually the same as the probability that y is less than or equal to 7. When you use the binomial CD on your calculator, it will always be for less than or equal to calculations. So to work out this one, we actually need to use the x value of 7 and not 8. So we'll go back into our distribution, change this x value from 8 to a 7, and then if we press OK and go down and execute this, we'll get this answer here, which rounds off to 0.2898. Here are 3 more questions for you to try. For this first one, we need to do binomial PD since we want the y value to equal 12. So we'll go to binomial PD, select variable, and change this value from a 7 to a 12. We'll go down and execute, and we'll get this answer here, 0.04255. For the next one, it's the probability that y is less than or equal to 10. This means we need to use binomial CD. So let's go back, select binomial CD, and variable, and change this value from a 12 to a 10. We then execute, and we'll get the answer, which is 0.8454. For the final question, we want the probability that y is less than 6, which is the same as the probability that y is less than or equal to 5. And since the cumulative binomial distribution only does less than or equal to's, we'll need to enter the value of 5. So we'll go back and change this value here from a 10 to a 5, and then we'll press OK, go down and execute, and we get the answer here. So it's 0.05646. Next we're going to look at a distribution where we need to calculate some slightly different probabilities. Take this distribution here z, and we're going to find the following probabilities. The probability that z is greater than or equal to 8, and the probability that z is greater than 8. Now we know the cumulative binomial distribution calculates probabilities up to and including a particular value. So for instance, we could find the probability that z is less than or equal to 8, no problem. But now that we have greater thans, things are slightly more complicated. The value of n for this distribution is 12, so it could take any value from 0 up to 12. Let's write those out. If we want the probability that z is greater than or equal to 8, we want any of the values that are 8 or more, so these values here. Now, another way of thinking about this is we don't want these values here. So instead, we could work out the probability of getting from 0 to 7, and subtract this from 1 to work out the probability of getting from 8 to 12. This means we could rewrite this calculation as 1 subtract the probability that z is less than or equal to 7, which we do know how to calculate with the calculator. So let's do this. We'll take the calculator, go into distribution, and we want binomial CD. Since we have the less than or equal to, we have variable, and we want this value here to be 7. N is going to be 12, and the probability of success is 0.44. We press OK, execute, and we get this number here. So this is the probability that z is less than or equal to 7, but we don't want this, we want 1 subtract this. So 1 subtract this number. Now to do this on your calculator, you're going to need to change back to calculate, so I'll press home, go back to calculate, I'll do 1 subtract, and then I can just press the answer button since this previous number is stored in the calculator's memory. So we end up with this number here, which is the answer to the calculation, 0.09876. For part B of this question, we want the probability that z is greater than 8, which means it will be any of the numbers that are 9, 10, 11, or 12, which means it's not any of the numbers from 0 to 8. So we'll use the same trick here by working out this probability of the numbers highlighted in red and subtract this from 1. So this is equal to 1 subtract the probability that z is less than or equal to 8. So let's bring back the calculator. We'll just need to go back into distribution, back to binomial CD, into variable, and we'll need to change this number from a 7 to an 8. If we execute that, we get this number here. So we need to do 1 subtract that number, and if we go back to calculate, and then do 1 subtract, and then the answer button, this will give us the answer to the question. So that's 0.03037. Now let's take everything we've learned so far and apply it to an exam-style question. In this question, we're told that Bill and Naomi go bowling every week. Over a long period of time, they discover that on any given frame, the probability that each of them bowls a strike is 0.43 for Bill and 0.38 for Naomi. We're asked to state suitable distributions to model the number of strikes each of them bowls in their first 9 frames. Now obviously, given it's this video, it's going to be a binomial distribution, but let's think about why. We need a fixed number of trials, and we can see there are 9 frames. We also need a fixed probability of success, and for Bill that's 0.43 and for Naomi 0.38. We need 2 outcomes, so they're going to bowl a strike or not bowl a strike, and we also require that each of these trials are independent of each other. So we're going to need to assume that, say, when Bill bowls a strike on the first frame, it's not going to change his probability of bowling a strike on the second frame. In real-life examples of things like this, it may not truly be independent. For example, if you bowl multiple strikes in a row, it might build your confidence. And also your muscle memory may be strong, so you remember how to bowl in a similar way. So we're actually going to do 2 distributions here, one for Bill and one for Naomi. So for Bill then, we'll say let x be the number of strikes bowled by Bill, then x will be distributed binomially, and he's going to do 9 frames, so n is 9, and his probability of success is 0.43. Then for Naomi, we'll say let y be the number of strikes bowled by Naomi, then y will be distributed binomially. It's still 9 frames, so n is 9, but Naomi's probability of success is 0.38. In part B, it says to state any assumptions that were made to use the distributions in part A. Now this relates to what we were talking about a moment ago. There are a few different assumptions that we could write down to answer this question. Firstly, we have assumed that the probability of bowling a strike is fixed for each of them. The question does say over a long period of time, which would indicate that there's been lots of bowling going on, in which case these values are fairly reliable. However, people's probabilities may change. They may get better at bowling, and therefore their probability could increase. So we're going to need to make that assumption. We're also going to assume that there are only 2 outcomes, so bowling a strike or not bowling a strike, and also bowling a strike on any individual frame is independent of the others, the thing we talked about earlier. For part C of this question, we're going to need to work out some probabilities. We need to find the probability that Bill bowls 4 strikes, Bill bowls less than 6 strikes, and Naomi bowls at least 4 strikes. So for the first one, which is Bill bowls 4 strikes, we're going to use Bill's distribution, so x, and therefore we want the probability of x to be equal to 4 for 4 strikes. So let's take our calculator and plug in these numbers. We go to distribution, Binomial PD for this one, down to variable. The x value needs to be 4. N for Bill's distribution is 9 for the 9 frames, and his probability of bowling a strike is 0.43. We'll execute this and get the answer, which is 0.2592. For the second part of the question, we need to find the probability that Bill bowls less than 6 strikes. So this is the probability that x is less than 6. Remember, we can't have a less than, we need to use less than or equal to's, so we'll change this to the probability that x is less than or equal to 5. This time we need to use Binomial CD, so let's go back and enter that mode. We want variable, and the number for x needs to change to a 5. So we'll press OK and go down and execute this, and we get this answer here, so 0.8634. For the final part of the question, it's Naomi this time, and she's going to bowl at least 4 strikes. So we'll use her distribution, y, and we're looking for the probability that y is greater than or equal to 4, since at least 4 means 4 or more. When we have a greater than or equal to, remember, we're going to need to do 1 subtract a less than or equal to. So we want the values to be 4 or more, so we'll subtract the values for 3 or fewer. So it's 1 subtract the probability that y is less than or equal to 3. So on the calculator, we'll need to do Binomial CD, and we're already in this mode, but we need to change x from 5 to a 3. But also, Naomi has a different probability of success, it's 0.38, so we need to update that too. And we'll press OK and execute this, and we get this value here. But we need to subtract this value from 1, so we go to calculate, and we do 1, subtract this answer, and we get this number here. So the answer to this question is 0.4669. Now we're going to have a look at some other complications that can happen in exam questions. Take this question here. A bag contains 1 red counter and 11 blue counters. Students are invited to select a counter from the bag at random and replace it after. If the counter is red, then the student wins a prize. There are 30 students in Mr. Maiden's class and each student takes part. State a suitable distribution for the number of students in the class who win a prize. So in this question, we're looking at the number of students who win a prize, so we'll let x be the number of students who win a prize. X will be distributed binomially, and since there are 30 students in Mr. Maiden's class, we're going to do this process 30 times, so n is 30. And for their probability of success, well, the bag contains 1 red counter and 11 blue counters. They need a red counter to win, so 1 out of 12 of those counters is red, so the probability of being successful is 1 over 12. Notice it's okay to write a fraction here, it doesn't always have to be a decimal. In part B of this question, we're told this. The probability that x is less than or equal to k is in between 0.25 and 0.99, and we need to find a set of possible values for k. So this question feels a little bit like it's in reverse. Rather than being given a value and then asked to work out a probability, we're told something about this probability and asked to consider the values. Let's use our calculator to investigate. For this one, we're going to need to use the Binomial CD, since it's the probability that x is less than or equal to k. Now for this one, the list option is actually preferred, because we can enter multiple probabilities at once. Let's use our x values from 0, 1, 2, 3, 4, and I'm actually going to go all the way to 10 here. N is 30 for this distribution, so we could go all the way to 30, but as you'll see in a moment, we don't need to go that far. So N is 30, and P is 1/12, so we'll type 1 divided by 12 here, and then if we execute this, it will do all of those probabilities for us. So these probabilities here are the probability that x is less than or equal to all of these values, so 0, 1, 2, 3, 4, 5, all the way down to 10. And as you see when we scroll down, the probabilities here start to increase, and by the time we get to 10, it's actually 0.9999, so very close to 1. Now if we write out all of these probabilities at once, it looks like this. So this number here is the probability that x is less than or equal to 0. Now, we require this probability to be in between 0.25 and 0.99, and this number is not. So the value of 0 will not work for k. This probability here is the probability that x is less than or equal to 1. Now, this number is greater than 0.25 and less than 0.99. so k could be equal to 1. In fact, it could be equal to 2, 3, 4, 5, or 6. Unfortunately, when we get to 7, the probability exceeds 0.99, so 7 is no good, and nor is 8, 9, or 10. In fact, any numbers beyond 10 will also not work. So what we've discovered here is that the k values could be any number between 1 and 6. Now this question does say find a set of possible values for k, so we're going to need to use set notation to write our answer. You may not have covered this yet in pure maths, so if not, forgive me, but you may need to look this up. We use these curly brackets for the set. It's the set of k values, which are members of the integers, such that k is in between the values of 1 and 6, and I'll use less than or equal to values because we are allowed 1 and we are allowed 6. For part C of this question, we're told that Mr. Vickers' class has 30 students, but he only has 3 prizes available. We need to work out the maximum number of students that he should let take part if he wants to ensure that there's at least a 99% chance he'll not run out of prizes. So we'll begin by defining his distribution first. Let y be the number of students who win a prize. Then y will be distributed binomially. For this question, we don't actually know the value of n. Even though there are 30 students in the class, we're trying to work out the maximum number of students that he should let take part. So he may not let all 30 students take part, so we're just going to call this n for now. Since they're using the same bag as before, the probability of success will still be 1/12 though. So now that we have the distribution defined, let's think more about this question. We need to make sure there's at least a 99% chance he's not going to run out of prizes. And remember, he only has 3 prizes available. So for instance, if 4 students won, he would run out of prizes. He wouldn't have enough to give every student a prize in that situation. So we need to make sure that the number of students winning prizes does not exceed 3. So we want the probability of y being less than or equal to 3. And we need to make sure that this happens at least 99% of the time. So this needs to be greater than 0.99. So in this question, we're just looking for different n values where this is true, and we want to select the biggest one since we want the maximum number of students. Let's take a calculator and think about how we're going to approach this. Since we have the probability that y is less than or equal to 3, we're going to need to use the Binomial CD. So let's go and select that distribution. We'll go to Variable, and our x value here is going to be 3. Now we don't know the n value, that's up to us to decide, but we do know the p value is still 1/12, so let's enter that. And then we'll go back up and we'll start to think about what we're going to do for this n value. Now there's no point starting n at 1 because if we have 1 student playing the game, we're obviously not going to run out of prizes since we have 3. In fact, if we have 3 students playing the game, we're still not going to run out of prizes, because even if they all won, they'd all win a prize and we'd have one for each of them. It's when n becomes 4 though that we could run into a problem. If all 4 students won, we'd run out of prizes. So let's start by making n 4 and see what happens with the probability. So if we go down and change n for 4, and then execute this, we end up with this number here. So we find that this probability is actually extremely large. It's very close to 1, and it's definitely greater than 0.99. So the value of n being 4 is acceptable in this scenario. What this means is if we let 4 students play the game, it's very likely that the number of winners will be less than or equal to 3, so we will be fine because we have enough prizes. If we increase the value of n though, and let more students play the game, this will change. The more students that play, the more likely we are to run out of prizes, so this probability, the probability that we are safe and have enough prizes, will begin to decrease. Let's change our value of n from 4 up to 5 and see what happens. So if we go back and change this n value from 4 to 5, and then execute this again, we get this number here, which is still actually very close to 1 and still greater than 0.99. So let's speed up this process. We'll keep increasing the value of n until it drops below 0.99. So let's go for n equals 6 and see what happens. That's still okay. What about n equals 7? That's still okay. N equals 8? That's fine too. N equals 9? That's also okay, but we're getting closer. N equals 10? That's also fine. N equals 11? That's also okay, but we're very, very close to 0.99 now. So let's see what happens if n is 12. Well, we actually drop below 0.99. This means our maximum possible value of n was 11, since when we used n as 11, the probability was greater than 0.99 as required, but when n was 12, it dropped below. So the answer to this question is that the maximum value of n is 11, So if Mr. Vickers wants to ensure that he's got a 99% chance of not running out of prizes, he should only let 11 students play the game. There's another type of question that does come up in exams that's quite tricky. Let's have a look at another example. In this question, we're told the probability that a biased dice lands on the number 6 is 0.31. A student rolls the dice 15 times, and we need to work out the probability that the student rolls the number 6 fewer than 5 times. Now, the first part of this question shouldn't be too difficult for you now. We could say, let x be the number of times a 6 is rolled, then x will be distributed binomially. We're rolling this dice 15 times, so n is 15, and the probability of rolling a 6 is 0.31. We're looking for the probability that the number 6 comes up fewer than 5 times, so we want the probability that x is less than 5, which is the same as the probability that x is less than or equal to 4. So let's take our calculator and work this out. We go to distribution, Binomial CD, variable, x for this one is going to be 4, and then n is 15 for the 15 times we're rolling the dice, and p, our success probability, is 0.31. So if we execute this, we get this answer here, 0.48133555781. Now the next part of the question is where things get more interesting. We're told that 8 students each roll the same biased dice 15 times. We're asked to work out the probability that exactly 3 of these students roll the number 6 fewer than 5 times. Now, you should see that this relates to the previous question. We're rolling the same biased dice, and it's still 15 times. And in the previous one, we worked out the probability that the number 6 came up fewer than 5 times for one particular student. But now there are 8 students. For this question, we would say let y be the number of students rolling a 6 fewer than 5 times, and remember there are 8 students, so y could be any value from 0 to 8. So y will be distributed binomially, n will be 8 for the 8 students, but what about the probability of success? Well, this is the probability that any of them roll the number 6 fewer than 5 times, which is actually just the answer to the previous question up here. So that number will be our new probability of success. So that's what we write in here. So since we want to work out the probability that exactly 3 of these 8 students roll the number 6 fewer than 5 times, we want the probability that y is equal to 3. So let's take our calculator and we need to go into Binomial PD, and we're going to need to change our distribution. So x is 3, we want the value to be equal to 3. N is no longer 15, it's 8 for the 8 students, and our success probability is actually on the answer button still. So if we press answer, we get that number 0.4813 and so on, and if we execute, we get this answer here. It's really important that you don't round off that answer and use the answer button on your calculator. Otherwise, if you put in, say, 0.48 or 0.481, you would get a different answer to the final answer to the question. So the answer to this question is 0.2344. Sometimes we get questions where we have to give an explanation of when we might not want to use a binomial distribution. Let's have a look at 2 of those. So in this question, Kira takes free kicks in training until she scores 1. Explain why the number of free kicks taken by Kira in training cannot be modeled using a binomial distribution. Well, one of the requirements for the binomial distribution was a fixed number of trials. Kira is going to take free kicks until she scores 1. So she might take 1 free kick, she might take 10, we don't know, it really depends on how good she is at scoring free kicks. So for this one, we can't use the binomial distribution because it's not a fixed number of trials, so that's exactly what we say. The number of free kicks taken, the number of trials, is not fixed. For a second question, we're told that over a long period of time, the attendance for a school is 95%. One day, the head teacher selects a sample of 10 students from a class in the school. We're asked to explain why it may not be suitable to use a binomial distribution to model the number of students from the sample who were present in school. Now for this question, you may want to use a binomial distribution. You could say that n is 10 for the 10 students in the sample, and the probability that one of them is present in school is 0.95 for the 95%. But the problem with a question like this is these trials may not be independent, especially since they're taken from a class in the school. For instance, if you're sat next to somebody in class who has a cold, you may not be too surprised to find that you have a cold the following week. So if students are in the same class and one of them is ill, there may be an increased likelihood that the other students in the class are also ill, and this would affect the probability that they're present in school. So for this one, we could say that the trials may not be independent of each other. For example, illnesses may spread between students who sit together in the same class. Now, the final part of this video is just for students that do AQA and not EDEXCEL. although the content covered will be relevant to your second year of study, so you may want to watch anyway. Let's return to the bias coin that we used at the start of this video, and the probability of heads was 0.7 and for tails it was 0.3. Instead of throwing this coin 4 times, let's imagine we throw it 20 times. So x will be distributed binomially where n is 20, and if we're counting the number of heads, the probability of success is 0.7. You need to be able to work out the mean, variance, and standard deviation for this distribution. Let's start with the mean. The mean is sometimes referred to as the expectation. If the probability of success is 0.7, then you would expect to get heads 70% of the time. So if we're going to throw it 20 times, we just want to work out 70% of 20, which we can do by multiplying 20 and 0.7 together. This gives you 14. So the mean, or expectation, for this distribution is 14. For the variance, we start in a very similar way. We take n, which is 20, and multiply it by p again, which is 0.7. However, we also multiply this by the probability of failing, so 0.3. If you do this, you'll get 4.2, so the variance is 4.2. The reasons behind why the variance is calculated in this way goes beyond the scope of this course, but you're welcome to look this up. The standard deviation then is always the square root of the variance, so for this one we would just square root 4.2, which will give you about 2.05. So the standard deviation will be 2.05. Let's just recap how we calculated those. For the mean, we multiplied 20 and 0.7 together, so we multiplied n and p, so the mean is just equal to np. For the variance, we also multiplied n and p together, but then we also multiplied this by the probability of failure, which is 1 subtract p, so it's np brackets 1 subtract p. And since the standard deviation is the square root of the variance, this will just be the square root of the variance formula. Now fortunately, if your exam board is AQA, 2 of these are on your formula sheet. So you'll see here under discrete distributions, for the binomial distribution, the mean and variance is given to you. You just need to remember that the standard deviation is the square root of the variance and you'll be fine. Let's have a look at how we can use this in an example. So for this question, we've got 2 distributions, and we're told the mean of x is equal to the variance of y, and we need to find 2 possible values for p. Let's bring back those formulas for mean and variance. We'll start with the mean of x and use this distribution here to work out its mean. So for the mean of x, we take n, which is 34, and multiply it by p, which is 0.16, and this gives you 5.44. Now the question's told us that this is equal to the variance of y, so for this distribution here, we'll work out the variance. The variance of y is equal to n, so 25, multiplied by p, which we actually don't know, it's just called p in this question, and then multiplied by 1 minus p, which again will just need to be 1 minus p. We don't need these multiplication signs here, so this is 25p bracket 1 minus p, which if you expand gives you 25p, subtract 25p squared. Now in this question we're told that the mean of x is equal to the variance of y, so these two are equal to each other. We now have an equation to solve to find the values of p. If we subtract 25p from both sides, we get 5.44 subtract 25p is equal to negative 25p squared. Then if we add 25p squared to both sides, we get 5.44 subtract 25p plus that 25p squared, and on the right hand side those 25p squareds will cancel, so we get 0. We can reorder these terms, and we have a quadratic equation to solve here. Now you are expected to solve these on your calculator in your A-level exam, so let's have a look at how we do this. Bringing up your calculator, we want to go down to equation, and then here we select polynomial, and the first one there, which is a quadratic. We'll need to enter the values of a, b, and c. A is 25, b is negative 25, and c is 5.44. If we then execute this, you'll see we get 2 solutions, 17 over 25, which if we format to a decimal is 0.68. And then if we execute again, we get the second x value, which is 8 over 25, which is 0.32. So our answers for p are 0.68 or 0.32. Thank you for watching this video, I hope you found it useful. Check out the one I think you should watch next, subscribe so you don't miss out on future videos, and why not try the exam questions in this video's description.